Hello.
Hello guys, we will wait for some more time, okay, so that your friends can also join. We'll start the program by 3:10. Okay.
Okay, sir.
Okay, sir.
Okay, sir.
Sir, when can we start?
We are starting soon. Okay. Just a second. Now you put it in the. So, good evening, all of you. We will be starting the class now. Uh, as you know, this is our Space Week. Space Week is celebrated globally from October 4th to 10th. And we in Regional Science Center and Planetarium had a lot of programs, and a lot of people have will be participating in the program. So today is the first day of the sessions. The first day we have a small introduction to space dynamics. So what I will do is that I will just introduce. You can always stop and ask question whenever you want, and I will try to answer. Or if required, I will say you that we will discuss it in the future. Otherwise, we will be answering as and when we goes. And this program is mainly meant for actually school students, those school students, high school students from class 8 and 9 onwards, 8, 9, 10, 11 also. So we will not be using much of calculus actually, because those space dynamics deals with calculus. We will take the results as the result as they are, and we'll try to discuss it. We'll not derive anything involving calculus, so that it is not difficult for either of all of you to understand. So anyway, we have a lot of people. So can anybody say me that what comes to your mind when you speak about space dynamics? Let us make it an interactive session instead
black
of
hole.
Launch of spacecraft.
the travel of spacecraft. That is fine. Anything else?
Sir, black hole.
Black hole is mostly about astrophysics, not about space dynamics, in the sense that dynamics
Sir.
means emotions.
Sir?
Yeah, tell me.
Sir,
Sir, launch and control.
sir, it could be the path of the spacecraft from where the spacecraft gets launched, so the path which it travels.
Yeah, somewhat like that. So
Calculations of how much fuel to use and how much to save.
yeah, fuel is also there, which is the best possible path. How do astronomers and space scientists actually calculate the best possible path? And if for example, there are certain parameters, if we
So launch control.
launch control is a very different discipline. It is something to do with rocket science. So we will not go into that aspect. We will in general try to deal with actually the dynamical aspects of any object in space, not only spacecraft. It can be a comet, it can be an asteroid, it can be any type of like our planets and or artificial launch satellites, how they work in this space. So we will be trying to discuss all these things. Most of you might have heard about Kepler's law of planetary motion. By the way, all of you are aware, no? How many planets are there in our solar system? Can anybody answer me?
Eight planets.
Eight
Sir, eight
planets.
planets.
Yeah, good. Eight planets. 8 planets are there. And did you hear about this person called Kepler?
Yes,
Yes,
sir.
sir.
Yes, sir.
Yes, sir.
Apart from this planetary motions laws, did he do anything else? Do you know anything about it?
Yes, sir. He's a mathematician too.
Yeah. Apart from that,
He was a
how-
mathematician.
So he's a musician.
Okay, yeah, he was a musician. He was an optician also, where in the sense that he had a type of telescope, optics of a telescope which he has designed. So they are called Keplerian telescopes. So apart from that, actually, this Kepler, no, he was working in somebody's observatory. He was an assistant of somebody's observatory. Do you know anybody who was that person under whom Kepler went to work? In Havens Island, he went to work in a certain astronomer's observatory as a young person. He wanted some work, and that person recruited him to actually look after his data. I will tell you if you are not. So the story goes like this: that there was an astronomer called Tycho Brahe. Tycho Brahe was a
Who?
Tycho Brahe. Somebody calls it as Tycho Brahe also. So we call it Tycho Brahe. Tycho Brahe was an astronomer, no, who was a very precise. Means his observations were very precise. He used to take very accurate measurements of the planetary positions and all through his instruments. He had lot of instruments. He has made lot of his designs and all. So with that, he had collected lot of data, and he wanted a person who will actually go through the data and who will keep a catalog of data, or who will help in recording the data. So he wanted an assistant. So he advertised for this post, and ultimately this gentleman, this Kepler, Johannes Kepler, he applied and he was inducted as an assistant of Tycho Brahe. And after some time, actually, the person, no, he was this Tycho Brahe was a very different type of person. He will not say Kepler why actually he is making all this data, what is his intention. He will not say all those things. But Kepler was a young person, so he wanted to know why actually this fellow is doing all these things. So ultimately, he said that I will resign the job and go. I don't want to, like a dummy, I don't want to work. So ultimately, as the story goes, that Tycho Brahe died, and Kepler got all the data. And for 16 years, for first 8 years, he has discovered. Means he took first 8 years to just jot down the first one law, what is known as the first law of planetary motion. I will say you about that law. And second, actually, after that, he made so then he discovered the second law, and after 16 years, he came out with the third law. So painstakingly, he did all the calculations, and ultimately, he came out. So we have the three famous laws of planetary motion due to Johannes Kepler, and they are called Keplerian laws. As somebody has already said that, see, in our solar system, there are 8 planets. Not only planets, we have asteroids, we have comets, we have dust particles. Everything is going around the sun. Now, why actually these planets move around sun? Can anybody say me? Why do you feel that the planets are moving
Because
around
of the
sun?
sun's gravity.
Due to sun's gravity.
So sun's,
Gravity.
yeah, so sun's gravity. So suddenly, if the sun vanishes, what will happen to these planets?
It will float away.
They will all lose their gravity.
Uh, they will not lose their gravity. They have masses, but they will see gravity is something like two bodies are there, or multiple number of bodies are there. Between each of the pairs, there will be some force. So if the sun is a very massive body, so what happens is that if the sun is somehow removed from there, all the orbits will be distorted, and since
They
these
will float.
objects, yeah, they will be
They
going
will-
around astray here and there and in straight, because they are moving
So
around.
they will become rock planet.
Yeah. So they will not move round like in an orbit. They will go in a different locations, and maybe they will be captured by some other star or something else, or minor objects can be captured by planets also. So a lot of things can happen. So basically, what I wanted to convey to you is that this gravitation, law of gravitation, is very important, because we will be discussing about that law in future slides. So what before that, what did Kepler do? Kepler actually found out with all these calculations and all this data, he tried to fit, because people were not that time fascinated with circles. So he was going on fitting circles, and circle within circle, circle moving on another circle, different types of things he were going on trying to find out how exactly the data were not matching. So ultimately, because he was predicting a certain data and looking for the observed data, that is the way actually science moves. So this prediction and comparison was not actually tallying. So ultimately, after a lot of research, he came out with something called an oval orbit, that is the elliptical orbit. That is though it is very simple, but it took a lot of time actually for him to pin down that the orbits of the planets are actually oval. So orbits of planets is an ellipse. So as you are seeing here in the slides, now this is a ellipse. This is an elliptical figure. So by seeing this figure, what all of you understand is how does this figure differs from a circle? Can anybody say me?
So it's an oval.
Oval. For example, in a circle, now we have, for example, when we take a circle, what comes to our mind is that it has a constant radius. So wherever from the center you take to the circumference, no, the radius, the distance will be
Will be equal.
distance will be constant. But let me do one thing before continuing. Let me show you one particular board. Say here. So I was just showing something like this. Okay, we are coming back. There was a loss in connection. I will come back to the wood now. Yeah, just a minute. Oh, fine. I think this one. Yeah. Yes, share this. Yeah, I will share the screen. Where it is. Everything, entire screen you share. Okay, so all of you can see the screen?
Yes, sir.
Yes,
Yes,
sir.
sir.
Yeah. So there was a loss in connection, no problem. So you see here, I am trying to draw something for you. So this is, it is not exactly what I want. Wait a minute. I'll try to draw a better circle. Say, so if I draw somewhat, imagine that this is somewhat like this in whiteboard. I am drawing in a digital slate. So this is the center. So what happens is that if you draw from the center, if you draw anywhere, no, from here to here, this distance is say x. So everywhere it is x. So that is the beauty. So this is called the radius of the circle, and we have the circumference and all those things. See, this is the center, and everywhere actually it is at a distance x from the center. So instead of that, if you have an oval, so let us draw an oval in this and that elliptical shape. So elliptical shape is somewhat like this. Say, let me complete it. Yeah, so it is somewhat like this. So if you do one thing, that if you cut a paper of this shape, and if you fold it in the axes of symmetry, say straight, imagine this is a straight line and this is another straight line. So if you fold it, though I think it has not come through the center, just a minute, I will try to make it through the center. Now if you fold it like this, you will see that what you will see is that this distance, say this distance is something, so let us call it A, and this distance is something, let us call it B. This distance from the center, this is the center, let us call it O, center, let us call it A, and this call it B, this call it C, and this let us call it D. So anytime when we start studying a curve, these are all curves, closed curves. So this is an elliptical curve. So we try to quantize, then only we can find out the equations and dynamics and all those things. So we have to learn about. So you have already studied something, but you may also study in future some more about all these curves. So what happens is that this particular part is, since it is long, see, it is long. This distance is long from the center to here, it is long. This is called a major axis. So this is called a major axis. And this part, if I put some other color here, this part is somewhat short compared to the previous part, and this we call a minor axis. Okay, so we have major axis, minor axis. Sometimes people also write it in a different way. Say if I take a rubber, just allow me to, sometimes the notations are different in standard notations. So let me reduce this size to a smaller size, so that I can erase a smaller portion. Sorry, here. So if I erase this part and if I erase this part, so I will just connect it again. So this I connect, this I connect. Sometimes people use this as A and this as B in standard notebooks. Though that depends on us actually. How do we define that? So this is exactly an elliptic curve, and this is what Kepler found out by painstaking research for 8 years, that a planet actually moves. So if this is a planet and the sun will be in one of its foci, there are 2 points in this major axis. These are called focus. The sun will be at one of these focus, either here or there, and the planet will be moving along this particular path. So this is what is the concept of this ellipse and the motion of the path. So let us move forward. So yeah. So Kepler's law states that the orbit of the planet is an ellipse with sun as one of the focus. Now you understand what is an ellipse, what is the focus, what is the center, and so. And then what it says, that the line joining the planet. So this is the planet. So line joining the planet to the sun. This line. So as it sweeps, no, it is sweeping. It is moving on the curve. So it is sweeping. So this particular area. So line joining equal areas. So, and this is a longer, though it is a shorter arc, but this area, this distance make it a long, means it appear as a longer triangle, but the areas will be same. So line joining the planet and the sun sweeps equal area. So these two areas, if you calculate, it will appear same. So similarly, because it is bigger here but shorter here, so this area and this area will be same. So equal areas are described in equal interval of time. So that is a very important result. So that gives us a lot of things that we will understand slowly, but this is one of the very important results. So this is the second law of Kepler, and the third law says that the time period, the period, for example, it starts from here, pass through this path and comes back here. So this time period is proportional to square of the time period is proportional to cube of the semi-major axis. So semi-major means half of the major axis. So this is not the semi-major axis. If this is the elliptical path from the center to the point, this is what I was showing you there. So that was the semi-major axis. So that is square of the time period is proportional to cube of the semi-major axis. So I hope I understood. You understood all these three laws.
Excuse me, sir.
Yeah. Tell me.
Sir, I did not understand the third.
Last
Last law.
Okay, last law. I will again. I'll do it in the board. That will be fine, I think. So let us do it something here. So I think you understood what is an ellipse. So what happens is that, let me draw it. So we have it here. So this is an ellipse. And first law says that it moves in an ellipse. Second law says that, for example, if we have the focus here, how do we draw the focus? That I have already said you. So if we draw the axis, so this is one of the axis, this is another axis. So these are the two axes, and say this is one of the focus. So focus, say there are 2 points. Now we will define focus and all afterwards. So there are 2 points on the major axis, but these 2 points are equidistant from the center. So that is very important. If I have drawn something different, that is my mistake, but it should be equidistant. So let me undo that. So we have, say, one focus is here. Say another focus is here. So what it says, second law says, is that if we take, so the planet is moving, say starting from here, it moves up till here. Say, let us call it as A1 and A2. So it has described this area, which we, let us call it as say delta 1. I am just using certain notations, don't worry about what I spell. So immediately this is A3 and this is A4, and we have the connecting the radius. These are called radius vector because this is taken as the focus. So this line joining the planet is here. It has moved up till here. So this is the area it has described in the motion, and let us call it say this area as delta 2. Now incidentally, it happens that delta 1 equal to delta 2, that is these two areas matches. The time for description of from here to here and the time for description from here to here exactly is the same. So what do you understand? Can anybody say me something more than what I have already said? I said that the time for description from here to here is same as time from description from here to here, in the sense that A1 to A2 and A3 to A4. Can anybody say me something more with respect to the orbit and the any other parameters? Can any more insight be put in this particular thing? Anybody?
So if the areas is equal, the
Yeah.
time proportional to it will be equal. Time taken to revolve around the sun.
Yeah, no, it will not be equal. It will not be equal. Anybody else? I said that the time.
Sir,
Yeah, yeah.
sir,
Somebody.
if A1 to A2 is equal and A3 to A4 is equal,
A1 to A2 is
then
not equal. No, sorry. A1 area described. If we call it as here as 0, this triangle, this say curvilinear triangle, say A1 0 A2, and this triangle which we are calling as delta 1. This area and area of this one A3 0 means O A4. These two are equal. Now tell me.
Sir, if delta 1 and delta 2 is equal, delta 3 and the delta 4 will it be
Yeah.
equal?
Delta. I have only done delta 1 and delta 2, meaning the areas of those sectors. So based on that, can anybody say me anything? Yeah. Any other comments?
sir, distance will be equal in other left areas.
Areas, no, just okay, I will just explain a little more. See here, what I am meaning is that, see, these areas are equal, and you can see from this figure is that, see, the planet has to travel from here to here in equal interval of time. So this time taken by from A1 to A2 and the time taken from A3 to A4 will be equal. What does this mean is that if the time is taken as t, okay, and if the time this is also equal, this what I am saying, as per law these are equal, so both are t. And the arc, let us take this as let us take this with some other, this particular arc, let us call it S1, and this arc let us call it S2. So obviously from the figure you can understand that S1 is greater than S2, isn't it? Because this is a bigger distance compared to this. So if we divide both sides by t, S1 by t means distance by time. What is distance by time? It is velocity, which direction is involved here. It is velocity. So see, these are moving in a particular direction, so it is a velocity. It is a vector quantity. Velocity, not the speed. We don't say it is a speed. So if we call this as v1, velocity 1 is greater than velocity 2. So here the planet moves faster, and here the planets move slower. So faster compared to the other. So this is one of the implications. Though equal area and equal interval of time, what does it mean? That velocity from A1 to A2 will be greater than velocity from A3 to A4. So this is one implication, very important implication, which you should keep in mind. And next, what was said is that the time period. What is the time period? For example, if an say, if I have a circle, so if say, this is a circle of radius say r, what is the circumference of a circle? Anybody?
360 degree.
Circumference. What is the circumference? Circumference is the arc. 2 pi r, isn't it? 2 pi r, circumference of the circle. That is the path. That is the path of that particular planet. So this is the circumference. And if it takes in time t, so the velocity will be angular velocity, will be 2 pi or velocity, not the angular velocity. Angular velocity is described in terms of actually the angle. So velocity will be given by 2 pi r by t. Okay, so in this case, actually, what is said is that is the time period. The time period, if you know the velocity, you can find out the time period as 2 pi r by v. So same logic. So now, if the planet is moving in an elliptical path, say this is the elliptical path, though my diagram is not perfect. So this is moving. Imagine that this is continuously elliptical. So this distance and this distance are known to you, and it is moving, and its time period means it starts from here, say a1, it goes here a2, it comes here a3, a4, I am taking some random points, a5, a6, and back to a1. So this is like a cycle. So it takes time t. So that is the time period. And as we have already discussed, that this is the semi-major axis. If this is the origin, this is the point, the farthest point from in the longest point, major point. So farthest distance in the orbit from the center. This is called the semi-major axis. So what the third law says is the square of the time period, that is time period into time period. This is called square of the time period, is proportional to cube of the semi-major axis, a into a into a. What is it called? A cube. So t square is proportional to a cube, or we can say t square by a cube is equal to constant, say some constant. So you can say something like this. You can, if you have 3 orbits, you can say that t1 square by a1 cube is equal to t2 square by a2 cube is equal to t3 square by a3 cube, and so on. So is it clear now, the process?
Yes,
It
sir.
will continue like that.
Yeah. Because, for example, one problem may be something that, imagine that the Earth's orbit is reduced in such a way that it becomes 1/10 or 1/10. Let us take it 1/10 of its present orbit. So what will be the orbital speed of the time period of rotation of the Earth? So of Earth around the sun, if the orbit is somehow squeezed. So in that situation, you can use, how will you use, any idea how will you do this particular say problem which I was just said? Did you
I
understand?
cannot understand the last part.
What I said is that, see, you know that Earth is moving around sun. It takes 1 year. Okay. Now, if I do something, some magic or something, so that the Earth's orbit is reduced such that its major axis is reduced to say 1/5 of its present major axis. So what will happen to the time period of the period of revolution of the Earth? Yeah. What will happen? Can anybody say me?
Will reduce.
How much? I said 1/5. So 1/5. So what?
Sir, the distance from the origin to the either side.
Yeah, you can use that time. You can again use this particular law. What I said is that t square, say t1 square by a1 cube is equal to say t2 square by a2 cube. Okay, so what I said is that say a1 is our the present orbit, say a, the semi-major axis, let it be a, and a2 is, I said, 1/5. So a1 divided by 5, and t1, say t is our t1, we know it is 1 year. So we want to know what is t2, what is the orbit of the Earth. So what do? We put here 1 square divided by, say, a cube is equal to t2 square divided by you have a by 5 whole cube. So it becomes t2 square into 5 cube divided by a cube. I am just reversing it, is equal to 1 by a cube. So if you multiply both sides by a cube, these two gets cancelled. Then we have T2 square is equal to 1 by 5 cube. So T2 is equal to 1 by 5 to the power 3 by 2. So this is the time period of rotation of our new in our Earth in the new orbit. So if our Earth's period is say 12 months, you put here 12 months by 5 into to the power 3 by 2, and you will get whatever is the answer. You will get that is the period. So that is the way actually we people start calculating and doing all these things. So now I think you got a flavor of what are the three Kepler's law, and they are quite relevant, and this is the way actually it is used. So that was the Kepler's law of planetary motion. Now, as I have already said you that there are certain, we have already seen in the whiteboard. See, Kepler's first law, we have already shown you that it moves in a ellipse. The ellipse are defined. We have a center. From center, there are 2 points called the focus. Sun is. It depends actually. You can consider any one of the focus as the point as the focus where Sun is residing, and the nearest point to the Sun on the orbit is called perihelion. This point on the major axis, the nearest point is called perihelion, and the furthest point is called aphelion. You should know all these names. Perihelion, when I say perihelion, it is the position of the planet nearest to the Sun when it moves in the orbit. Similarly, aphelion, the position of the planet furthest from the Sun when it moves in the orbit. And then we have the semi-major axis. We have the minor axis is not important here. And something is called as eccentricity. Eccentricity is defined as something like CS by C, means the distance from the center to the first focus, CS, by CA, that is center to the means a major axis. So center to the perihelion or aphelion, that is the major along the major axis from the center. So this distance. So that is the way actually these things are defined, and we will be coming back. So you can see that this plus this. So if you RA, what is the RA? RA is these are the, because these are the radius vectors. Radius in the sense that from the Sun to any points on the planet. These are if I radius vector, I will try to make you understand. That is quite an important concept. Yeah.
Can you repeat what is eccentricity?
Yeah, I will repeat. Just a minute. Let me just clear off this one. I will repeat it. So eccentricity is a measure of the ovalness of an orbit. How oval, how much, see, for example, there are different types of elliptical orbits. Let us say, what is the difference? Let us take, this is an elliptical orbit. This is quite, if I make it bigger, so this is an elliptical orbit, though it is not perfectly coming the shape. Imagine that if I sometimes it may happen that this is an elliptical orbit. You can see this major axis is big, major axis is this one, minor axis is small, minor axis. But in this case, we have a major axis, we have a, so these are minor axis. So what is major? If you take the red mark, this is the major axis, this is the major, and this is the minor. This is major and this is minor.
Sir, will always be the orbit in oval form?
No. Orbit can be in many other forms. They are a part of a conic section. We will be describing it. It depends on certain parameters. For example, if you are having a cone, let me put it in a different way. Just a minute. You have asked a very good question. So let me try to define different types of orbit. So when we study about orbit, which I will describe in a fair detail. So if you take two cones and keep it upside down, just take two cones and keep it like this. Imagine that these are, don't see my beauty of my diagram, it has not come well. So anyway, and if you take a plane, what is a plane? It is means if you take something like this and you cut this cone, say like this, parallel to the base. So what happens is that the intersection of this plane and the cone is a is a circle. So this is a circle if it is parallel. Similarly, if you take the cone and cut it in an inclined way, say if I cut it in an inclined way, so this is, then what you get actually the intersection as not a circle but an oval. So this is an oval. Similarly, I'll draw the oval in a better way. It has not come out better, so let us draw it once more. So this is, imagine that this is a plane and we have the oval here. So this is oval. So this is not a circle, this is an oval. Similarly, what will happen is that if you have a plane which cuts the upper half like this, something, maybe like this, something it cuts. So what do we have? The intersection is somewhat different. It is somewhat like what do we have is somewhat like this. So this is called a curve called a parabola. This curve, no, this is called a parabola. Similarly, what if we have a plane which intersects both sides? Let me take a different color. So it intersects both sides somewhat like this. Sorry, it goes like this. If we catch it like this, so you have two sections here, two branches, one here and one in the bottom. So there are these types of curves. I am drawing the plane actually. These are the two curves. This is one curve and this is the second curve. These are part of what is called as a hyperbola. So we have different types of conic section. One is a circle, one is a parabola, one is an hyperbola, one is after this parabola we have the ellipse, and one is a hyperbola.
So will the major and that minor will be increasing or decreasing?
No, the thing is that if it is an closed curve, somewhat like this, it has something called, as I was telling, it is a major and minor axis. Okay, sometimes it if it is a parabolic curve, something like this. Okay, so then we have an axis, and we don't call it as a major and minor. We have axis and directrix. There are two axes based on which this curve. So for example, a comet. A comet comes. We have a let's say a sun here. Let us think that this is sun, and we have a comet coming like this. It goes and then it passes. Say from here it passes. So the comet comes and it deviates because of the gravitational force of the sun. So what happens is that this is the comet coming. So this is its tail. So it comes like this. It moves like this. So like this. So ultimately it comes here and then it moves. So in this case, what happens is that we don't call the major and minor axis, because these types of curves are defined with respect to certain axes. So we have, say, if I have here two axes, so let us call it one axis is like this, one perpendicular axis goes say like this. So we have axis, this is called axis, and this is called directrix. So these are actually, if you study conic section in fair detail, you will study all these things. So for planetary motions, mostly we are confined to closed orbit. But when we study satellite motion, cometary motion and all, it can go in hyperbolic orbit also, it can go in parabolic orbit also, it can go in diverse different orbits. It depends on certain velocities, in the direction in which it is its mass and the direction in which it is moving. So all these things, that all we will discuss.
Thank you, sir.
Yeah, I think this part is clear. Now let us move forward. So this is what I was telling. So we have the eccentricity. Eccentricity is a measure of
What is eccentricity?
Yeah. Eccentricity, you asked me. Yeah, I will tell you. Eccentricity is something like this. Just a minute. I will just clear off this one. Let me clear the board. Make space for me. So when we have a curve, what happens is that. So let us draw it here. So if we have an axis like this and a perpendicular axis falling from here, and if there is a point, say if we call it as a focus say S, let us call it as S, and this is the variable point, say P, which is the point which moves along the curve, and if we join these two PS, if we join, we get a line, straight line, and if we draw a perpendicular from P to this particular axis, this is called the directrix. This should be perpendicular. Let us call it M. So this is the axis, and this is called the directrix. They are drawn. So this ratio PS by PM is called eccentricity, E. That is eccentricity E. So we have for a circle, E is equal to 1. This is for a circle. For circle, and then we have parabola, E less than 1, and hyperbola, E greater than 1. So like that we have different eccentricity, a circle or parabola, this ellipse. Ellipse is a special case of a circle. So we have for this, say, let us not, when we for in this circle, actually A is equal to B, that is major and minor axes are the same. So for ellipse we have the eccentricity is equal to 1. For parabola we have less than 1. For hyperbola we have greater than 1. So this is the concept of eccentricity. Did you follow it?
Yes, sir.
Yes, sir.
Yes, sir.
So now, so this is what I was telling, that this is about the first law. So we know about eccentricity. Now this is the focus. You can understand that, see, if this is RA is what? From the sun. That is from one focus to the aphelion. You know that this part is A. This is the major part. This is A. This is A. See the arrow. What I am drawing, this is A, and this part is AE. So this distance is AE plus A. So if you take A common, 1 plus E. Similarly, if you want to find out this distance, you have to subtract this RP from actually the distance of the semi-major axis. So the semi-major axis is A, and this RP is AE. So AE is this, that derivation can be done as I have shown you from the definition. So naturally this is A minus AE, this particular distance. So that is the way these are to define here. Now, the second law of Kepler, as I was telling you, that it describes equal area in equal interval of time, and that is what is shown here. This area and this area, time taken from P1. Say it reaches, it starts from here. At T1 it reaches P1. At T2 it reaches P2, and at T3 it reaches P3, and T4 it reaches P4. So the time taken from P1 to P2 is T2 minus T1. So this is the time taken, and similarly from P3 to P4 it is T4 minus T3. So these two times, these are equal times. So and these two areas, equal areas. So this area by this time is a constant. So that is what is the second law is all about. And we have, as I was telling you, that we can derive the third law also. And this There are some minute derivations. We will not go into this detail because this is a bit complicated, so it requires some more time. Angular velocity and all those sign and all, we will not go into those mathematical details. So let us stop here. And this third law I have already explained to you. It is that cube of the semi-major axis is proportional to the square of the time period interval. So these are the three laws which are very important. So with these three laws, actually what we can find out, we can find out the velocity, we can find out the orbit, but still actually we don't know. In fact, Kepler also didn't knew why should actually the planets go around the sun. What is the necessity for the planet to go around the sun? What is making it to move around the sun? That was not known. They only know the kinetics part of it. The kinematics, that is the forces and all those things were not developed at the time of Kepler, and that got developed actually after Galileo did his experiment, and ultimately Newton formulated the law in his Principia. So then actually Newton, with using Galileo's results and Kepler's laws and all those things, he gave a backing through his own theory, which are called the Newton's laws of motion. So all of you know Newton's law. You have studied Newton's law, isn't it? All of you have studied, no? Newton's law.
Yes,
So,
sir. Yes,
so,
sir.
so according to Newton's law, Newton's first law, if you take a ball and if you just kick it, what happens to the ball? Can anybody say me?
Sir, after some distance it will stop.
After some time it will stop. But first law, what does it say? Every body means any ball or any something like that. Every body continues to be in a state of rest or of uniform motion in a straight line insofar as it is compelled to change the state of rest by an external impressed force. So don't you feel that the ball should have gone far away, where it should never have stopped? Why it is stopping?
Because the
Because
gravity
of
pulls it
friction.
down.
Because of the friction.
Gravity.
Frictional force.
Yes, correct. The gravity is not the correct answer because the ball's mass is so small compared to Earth's mass. Gravity is very feeble. What is happening here is that the frictional force, the friction between the surface of the ball and the ground, it makes it so. So this is actually what is said in the second part of the first law's last line. It is compelled to change the state by an external impressed force. Here the external impressed force is actually the frictional force between the ground and the ball's surface, and that makes the ball to stop after a certain time. So that was the first law. The second law is that the rate of change of momentum is proportional to the impressed force and takes place in the direction in which the force acts. So rate of change of motion, that is actually the what we will see is that this, yeah, tell me.
Sir, what is the meaning of momentum?
Momentum is a term which is used in physics, which is actually a product of the mass and velocity. Okay. If you take mass is a quantity, what is mass? Mass is amount of matter contained in the body. And what is the velocity? Velocity is the displacement by time. Displacement has a directional aspect. So if you take the mass is having no direction, it is just a quantity. So if you multiply quantity like mass with velocity, you get a certain measurement in physics which is called as a momentum. It is one of the important measurements which is used. So we have the momentum. So what it says is that the rate of change of momentum, that is momentum at one place. So rate of change means, for example, let us try to understand this part. This is quite important for your school also. So we will spend some time in this one later. So this is quite interesting. Let me erase all this fast. Yeah. So this has gone. So now let me take a finer tip and. So what I said you is something like this. What is momentum?
So we can't see the screen.
You can't see?
No, sir, we
We
can
can see
see.
only the wallpaper.
Can't you see anybody? Nobody
No,
can
sir,
see?
we can see. We can see.
Sir, I can see.
Yes, sir, we can see.
There is some problem with you. Maybe I will write a little bigger. I think that I have written smaller. That might be the problem. Wait a minute. Okay. Let me write it here. See, momentum. I think you can see now this is fairly big enough. Momentum. momentum is equal to mass into velocity. Okay, so momentum is mass into velocity. Velocity is what is velocity? Velocity is quite velocity.
Displacement by time.
Yeah, velocity.
Displacement.
There is a difference between speed, what you see in your car, bike, and all those, speed and velocity. There is a
Yes, distance by time.
yeah,
Vector and scalar
And,
quantities.
yeah,
and velocity is displacement by time.
yeah. Speed is actually distance by time,
Distance by time.
distance by time,
And it is a scalar quantity.
yes, because it doesn't have a direction, correct. And we have the velocity is equal to displacement by time.
Sir, it's vector quantity.
It is a vector quantity.
Because it has magnitude.
And direction. A magnitude and vector quantity has a magnitude and direction both. So so speed is a scalar quantity, velocity is a vector quantity. When we multiply a scalar quantity with a vector quantity, we get something called a vector quantity, because it also magnitude has a, so normally momentum is represented in physics as the letter P. Small p is equal to m into small v. Vector is represented by an arrow above that. So this is the way actually we represent p is equal to mv. Okay, so these all things you will learn when you study in class 12 or something like that, 11, 12. Or in your physics book also it may be said, in 9, 10 also it is said that what is a scalar. And so this is the momentum. So what is said in our second law is that the rate of change of momentum, that is, if a certain time, say t1, the momentum is p1, and t2, the momentum is p2. Okay, sorry, let it be p2. So we have the change of momentum is how much between t1 and t2? Say p2 minus p1. And rate of what is the duration in which it has changed? So the t2 minus. If you divide these two,
T1.
if we divide these two, we have p2 minus. I'll make the change. Say this one, fine. So we have p1 here. So we have p2 minus p1 divided by t2 minus t1. So this quantity is called rate of change. Rate of change means change with respect to time. Momentum is changing with respect to time. So if for example, if this t1 and t2 are going near, so if we have say t1 is here, first t1 we put it here, and t2 we put it here. They are quite far away. Next, say where we put t1 to half this place, say t1 dash, it is half. So next we come to nearer, so we go on coming t1 double dash. So if we come more closer, so say more closer, half of that. This is called Zeno's paradox. So if you will study about it, you can look the internet. So you go on coming near, still you can never reach t1. So like that you go on coming near, no? So this is called an infinitesimal quantity. So it comes very near. In that case, we write as delta P by delta T. So these are very close points where momentum and time are taken. So if you try to make the time tending towards zero, if delta T is tend towards zero, so this goes as a limiting concept, then we write it in calculus notation as dp by dt. And this is what is rate of change of momentum, and this is proportional to actually the force impedance, that is mass. So from this you can derive by calculus and all those, we will not do today. Force is equal to mass into acceleration. This is a consequence of the second law of planetary, Newton's second law, mass into acceleration. What is acceleration? Acceleration is
Rate of change of velocity.
Yes. So we have a mass. Acceleration is rate of change of velocity. So this is a vector quantity. Vector quantity. Let us. I will do one thing. I will write it in a. I will write this in a different color. So this is vector quantity. Similarly, this is so mass. Our scalar is multiplied to a vector, so force becomes also a vector quantity. So we have force is equal to mass into acceleration. So this is the second law of Newton. So very important. Okay. So we have these two laws, and then we have the other one, which says that what does it say? It says that every action there is an equal and opposite reaction. Now, for example, say you are trying to let me say you a paradox. Say, for example, you are sitting in a table, and the action is action and reaction are always there. So you can never get up from the table or from the chair, whatever it is. So still all of us can get up. Why does it happen? Can anybody say me? See, action. What is an action? Action is some type of force which is going in one direction, and reaction is an opposite force, which is, so when there are two bodies, for every action, for example, if a stone is kept on a ground, there is an action is there, the weight of the stone is towards the ground, and there is a reaction from the ground. Actually there is a force which is trying to keep the stone in its own place. That is the reaction. Action and reactions are equal and opposite. So this is these are the consequences of the three important laws of Newton, which are very important for Newtonian mechanics. So which you will again do lot of problems and study. Yeah, tell me.
Sir, the third law, in short, we say that every reaction has an opposite. Every action has an opposite.
See, for example, if you are firing a rocket, all of you have fired in Diwali or some other occasions, you have fired a rocket. So you have seen that when you fire the rocket, what happens is that gas comes out of the rocket. All of you have seen, or in our normal ISRO rockets also, or NASA's rockets also, you have seen that the gas comes out. So what happens is that the gas is coming out with a force, as a result of which the rocket is moving forward. So action is on gas coming out is action, rocket moving forward is the reaction. So equal.
Sir, is it was that we can get up from the table because the reactional force is lower than the actional force?
No, it is not lower. The thing is that action is given by the body on the, if you are sitting on a chair, for example, your weight is falling through your center of gravity of the body, and it falls on the chair. But when you try to get up, what happens is that you press your feet on the ground. So reaction is coming. So there is a couple forming, and that makes you get up. Okay, so that is a bit tricky.
Okay, sir.
Yeah, that is a bit tricky. Yeah, so that was the Newton's three laws of motion. And then Newton did one more marvelous thing, which actually gave a new view to the whole space dynamics and astrophysics and all those things. He devised the law of gravitation. Universal law. Why it is called a universal law? Can anybody say me? Why this word universal is used here?
The universe.
Yeah, no, it is not about universe. Universal, see, universe and universal are two different things.
Every object in the universe.
Every object.
Yeah, the universe in the sense that this law is not only applicable on Earth, it is applicable for any two mass separated by a distance, anywhere in our universe. So that is, it is applicable. This law is valid. This law, this Newtonian's law, for so we should not take into the very small distance where actually we have the electrostatic forces coming into, like our special theory of relativity and all. We should not take, but in a vast area, means where our electric forces and quantum forces are not acting, where only masses are there and the gravitational forces are there, for any two objects, say stones, balls, planets, comets, stars, whatever it is, any two objects or any multiple objects taken two at a time, if they are separated by a distance r, then the force between them is proportional to the product of the mass and inversely proportional to square of the distance. So this law is valid everywhere, and this gravitational constant has been determined experimentally, and it is equally holding for any of this Newtonian thing. But when it goes to a very large scale, like if you have many galaxies and all, then again this law has to be modified because of certain other physical things, new concepts coming up, because this is on a Newtonian plane, because in a plane it occurs. So in that case we have the Einstein's general theory of relativity. So that is for a very large scale. But for our terrestrial purpose or nearby the solar system and all those things, our Newtonian's law holds very good. So this is a universal law. It says that the product, if we have two masses or any number of masses, you can take two masses at a time, and then the force between those masses are proportional to the product of the masses, directly proportional to the product of the masses, and inversely proportional to the square of the product of the masses. So this gives the law. So this is very important, which you will be using it. Okay, and this is the way which is why actually, see, we have a planet, we have the sun. Sun has a mass, same mass of the sun. Planet has a mass of the planet, and the planet moves around the sun. So we have the product of the mass, the distance separating, and we have the force, that is the gravitational force between the mass, within the planet and the sun. So like that it moves. So similarly, you can see that here we can calculate the orbit of the moon. In this case, some calculations are shown. Again, we need not just now bother about all those things. So this I am skipping again. It is a bit involved. And then there is a class of problem in physics. Again, it is a bit. It requires a separate class to discuss this particular thing. Whenever two bodies are there, we can actually calculate the motion of the two bodies with respect to one another. So that is called as a two bodies, because if we have many bodies, the influence of each body on the other can be taken, but we can actually calculate the motion of two bodies at a time, and ultimately you can reduce from these two. Just a minute. I think I have come back in physics. Okay. Yeah. So we can actually derive the laws of two bodies. I will just tell you how it looks like. When you have, there are certain equations which are formed. You can take two bodies. If there are a large number of bodies, you can pair the bodies and then you can combine the equations. So, but most of the cases of planetary motions, like we have a satellite which is launched from the Earth and it goes around the Earth, or it goes to the moon in a certain orbit. What type of orbit, I will just show you the graphics of it, but it goes like that. So like that, actually you can go on developing the kinematics and kinetics of it. So how does it look? Let us see here. So what happens is that, again, I will try to erase the thing. Just a minute. Erase all these things. So we have certain things like this. Yeah. So it appears like this. If you draw the equations and find out the solutions for that, we will not go into the derivation and all. It comes something like this, that half of v square minus mu by r. I will tell you what is it. Is equal to a constant. So what is this r? Say if there are 2 points, say sun and planet, say P. If is a planet and they are separated by a distance, say r, and the velocity of the planet with respect to sun, let us call it capital V, and this is r, this is v, and what is mu? Mu is a parameter which is equal to universal law of gravitation g, and say mass of the sun and mass of the planet. So it need not be sun and planet, as I said you, it is a general law. So we can put as M1, M2 or something like that. Just for your understanding, I put it. So this is a very important law, a law of two-dimensional, means two body problems.
Can you tell?
Yeah.
Can you tell
Which once more. Okay, once more. Okay. So we have say we have one body. Say one body. Say one body one, and we have one more body, body two. This body's mass is say m1. This body's mass is say m2, and these two bodies are separated by a distance say r. So if you have something situations like this, and don't see my drawing because I am drawing in digital pen and also it is going here and there. So anyway, so we defined a quantity called mu. Mu is equal to the universal gravitation. You know the capital G is where? Capital G is that our Newton's laws, it says that force between two objects is equal to universal gravitational constant, which is a constant. It is having a definite value, and then the product of the masses of the body by the square of this distance separating this. So this is a universal law, Newton's universal law. So we have these two. So from here, using this law and all, this motion of the two bodies problem is this one. So half of velocity square minus mu. Mu is this one, mu into m1 plus m2. That's what I was going to write. M2 is equal to a constant. So it is a constant. So those things can be found out, and RIM. So one thing you just try to understand from here. Yeah. Anybody? So this part. So
it is m1 into m2.
M1 plus m2, not into. G into m1 plus m2. Okay. And this part, can anybody guess what it looks like? This part? I'll give you an example. Means, anybody has come across this type of expression in your book? Half
Or
of
kinetic energy.
kinetic energy. Good. So this part, if you take the unit mass, if you because if the mass is constant, you can take it as a unit mass, divide by constant by mass. So this becomes a skeletal equation. So this is the kinetic energy part, kinetic energy part of it, and this mu by r. Minus mu by r, that is attraction, so minus it is. This is the potential energy. Potential energy. So what does this equation indicates? Can anybody say me? You have studied the conservation of energy. What does the conservation of energy says? Total energy of a system is constant. So kinetic energy plus potential energy is equal to constant. So that is what this this particular equation try to convey, and this is the equation which we get. And of course we can find out the for example, I will just give you one or two results, so we can always extrapolate all those results. Just I will erase these all parts. Okay. So I will not go into very detailed mathematics and all those things, so that I'll keep it simple, so that if you are interested, you can always study more. So for example, as I was telling you that this object, no, it moves, a planet is moving in an orbit, and say the sun is here and the planet is here. Planet is nearest to the sun and in this point, and it is farthest here. Let us call it capital A. So this, what is P? You know that this, I said you, this is called perihelion. Peri means nearest. Perihelion. Helion is standing for the sun, Helios. So perihelion, and this is called aphelion.
Aphelion.
Aphelion. And here the planet, let us
So
take
helium.
aphelion, aphelion. Okay, so here let the velocity, so if this is the line joining the perihelion, aphelion and the sun, at these 2 points the velocities are perpendicular. So we have Vp is the velocity here, and we have Va, the velocity here. And at these 2 points, actually there are by second law of our this one, Newton's second law and all, we can find out. We will not derive now, just accept it, the result. V is equal to R omega, where R is the separation between the, this is if the planet is here, see the distance planet varies. So the say, let us call it as P on. So this distance, let us call it R. It varies as it moves. This is R.
Sir, V is equal to
V is equal to R omega. This is this. No, it is not a W actually. It is somewhat like this. It is a Greek alphabet. It is called omega. Omega. Okay. So it is called omega.
Sir, is it a
It
value?
is a value. No, it is like, we have alpha, beta. Now, these are all Greek alphabets. Gamma. So like that. No, you have A, B, C in our English. No, we have A, B, C. So they are in Greek. They use all these alphabets and they have their language. But in mathematics, many of these Greek alphabets are used for our calculations and all, because of it is used. It has been used for long because Greeks were very learned people, so we have used their alphabets. So we have velocity is equal to R into omega, which applies at these 2 points because the angle between this velocity and the radius vector in these 2 points are 90 degree. So why it is so and all, it is a very different, it requires certain explanation which can't be done simply with a one line. So I will again skip this. So just have it for the timing that these triangles are 90 degree at these 2 points. At other points it is not 90 degree. So at this perihelion, aphelion, it is 90 degree. So velocities are perpendicular to the radius vector, and this holds there. And one more law which holds there, which is coming from the Kepler, is the Kepler's second law, is R square omega is equal to h. So the h is a constant, r is the radius vector, omega is, as I have said you. So based, if you take this and this, for example, if you eliminate omega from these two, from here what you get, I will just not to bore you with lot of maths, but I will just write here for some people. So v is equal to omega r, and if you have r square, v by r, if you put here, is equal, h is a constant, some constant like g. So we have h, it is a momentum vector, I mean it's a angular momentum vector. So we have this one r, and this cancels, and we have h is equal to rv. So we have this, or v is equal to h by r. Okay, so what is the aphelion? We have, do you remember this? What is this distance? What we said, this major semi-major axis minus AE. So this distance is A minus AE. So this is A into 1 minus E. Similarly, what is this distance? This from here to here. This is A, and this is AE. So we have A plus AE.
A.
Yeah, that is equal to A into 1 plus
A into 1 plus E.
Yeah. So we have, if you have, so if you can calculate velocity Vp, what is Vp? Vp is equal to h is a constant by Rp. What is Rp? This is Rp. This is Rp, radius vector at perihelion, and this is Ra, radius vector at aphelion. So we have h divided by A minus 1 minus E, and similarly we have VA is equal to h divided by E into 1 plus E. So we have, so if you let me take a different color. So if you then divide something like this, what is VA by VP? So simply by simple algebra, you can see that this is h by I'm sorry, h. Let me erase this. Yeah. This also let me erase. Now let me take this scale and let me take this point, say here. So this becomes A into VA is, what is VA? 1 plus E. 1 plus E divided by H by A into 1 minus E. So this becomes 1 minus E by 1 plus E. So so we have a simple relation where ratio between velocity at aphelion and velocity at perihelion is nothing but the ratio of the eccentricity. If you know the eccentricity of the orbit, you can find out the velocity. So this is a very interesting relation which we have. And similarly, actually, you use this particular, no, I have given you one more. We have seen that there is one more law, which is the combination of kinetic energy and potential energy, which is that v square by 2 minus mu by r is equal to constant. So we have velocity at perihelion square by 2 minus mu by radius vector at perihelion is equal to constant. And similarly, we have velocity at aphelion square by 2 minus mu by radius vector. So like that, you can go on calculating, and ultimately with all this reduction and all, you will get one more result. It is something like this: v, velocity of aphelion into velocity at perihelion, is equal to mu by a. That is semi-major axis. So this is one law, this is one thing, and this is another result. So using these two results, actually you can calculate VA and VP, so velocity at perihelion and velocity at aphelion. So these are some of the beautiful things you can go on trying and playing with it. So that is what I wanted to show you. Now, yeah. So like that, we can do certain things. So this was what I was discussing. So in many body problems, you take two bodies, and it gets more complicated. Instead of two bodies, you can have many bodies, and a lot of planets are there, a lot of asteroids are there, rings of Saturn, or many things are involved. So you go into complicated problems. So these are done at research level and all. And similarly, see how it orbits. I will just show you before ending how they orbit. For example, if you want, this is Earth, and you want to put the thing in a separate orbit. So what is done is that you go to, you start from the perihelion of you fire from here the rocket, and then you end up in the other orbits one path. So say here. So in this way, you can inject it in different orbit. This is called an Hoffman's orbit. So you make a parabolic. So this is the focus. So this is the aphelion point. From here you fire it, and then you fire one more rocket at the. I'm sorry. This is the perihelion point from which you fire it. So it goes and it transfers to then aphelion point. You again fire one more rocket. So ultimately it goes in a larger orbit. So this is the way actually spacecraft transfers to bigger and bigger orbit. Similarly, if you want to, for example, we are around Earth. A satellite is around Earth, and you want to put it in around Moon. Moon is at a distance. So first you put it in a round orbit around Earth, and then again you, if this is Sun here, this is Earth here, and we have Moon, or if we have a Earth here, many configurations can be done. So you are putting the orbit, first the satellite is put in one parking orbit, then again it is fired from here, it takes a trajectory. See this distance, this is the focus. So this distance is at aphelion point, this is the perihelion point, A is perihelion point, C is the aphelion point. From here actually it is fired, and ultimately it goes to the aphelion point, and then again you fire it, and then you transfer it. So this is the way actually spacecraft are transferred from one orbit, and calculations and all can be done in that. So this much only I think I had to convey today. Then if you have any other questions, you can always ask me. Yeah. You can put the questions in chat box, or you can unmute and ask me if you have any such thing. I will just stop presenting whatever I was there. So now, yeah. So any other questions before we conclude it? Did you understand something at least from this? What is space dynamics? What has to do with the Newton's law, Kepler's law, and Newton's law of gravitation? I hope you got
Yes, sir.
idea about it.
Sure.
Yeah, so now you can go through your books, your textbooks and other resources, and ultimately solve a lot of problems, simple problems. Try to solve simple problems so that you get used to how to calculate and all those things. And then I think you will, all of you will learn a lot about all these things. Okay, so let us stop here. Bye.
Thank you, sir.
Let us stop.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Okay.